Real-time feedback into the behavior of your distributed systems and observing changes, exceptions, errors in real time allows you to not only experiment with confidence, but respond instantly to get things working again.
Hello everyone and welcome to my talk, Lyra, Disrupting Full Text Search Industry with JavaScript. Before we start, I always like to introduce myself very briefly. I am Michele, I work as a staff engineer at Nearform, I'm a Google developer expert and a Microsoft MVP. I want to start by saying that I love Elasticsearch. When I think of full text search engines, I always think of my favorite open source project ever, which is Elastic. In the past, I had the opportunity to work a lot on Elasticsearch, or with Elasticsearch, of course, on projects and products. And I gotta say, I also tried working with Solar. I tried working directly with Lucene, so the library underneath Elasticsearch itself, but also underneath Solar. But I gotta say, every single time I come back to Elasticsearch because it's just an amazing open source project, and I truly, truly love it. In the past, of course, I've been contributing to open source a lot, and I've been working a bit on Unomi, which is a CDP, a customer data platform from Apache, that uses Elasticsearch as a leader database in the whole overall architecture. And I was amazed by the fact that every day we could just throw millions of data to Unomi and Elasticsearch would work just fine. And the performances in search couldn't be that much affected by the amount of data we just insert into the database, and this is truly amazing. And one question I always wondered was how is it possible that Lucene and of course then Solar or Elasticsearch can be that fast? And when we think about performances, when we think about how Elasticsearch, how Lucene works, we have to make a distinction. Of course, we already anticipated that a couple of seconds ago, but yeah, Lucene is the actual full text search library, which is written in Java, and Elasticsearch is not just a search engine itself because it uses Lucene, but it's also a RESTful server. It is a distributed system. It adds sharding on top of the overall distributed system, so that if you have a lot of data, you can shard data amongst multiple nodes. It takes care of data consistency, monitoring, cluster management, a lot of stuff. And as I already said, I love Elasticsearch, and I wanted to start recreating it from scratch, not because I didn't like it, but because I wanted to learn more. And quoting one of the best of all time, Richard Feynman, what I cannot create, I do not understand. So that's my life motto. This is something that truly explains the way I do learn stuff. So yeah, I wanted to create something in order to understand how that works. Of course, again, I love Elastic, but I also had some problems with it. It's not the easiest software to deploy and set up. Let's be honest with that. It's quite hard to upgrade. It has a big memory footprint, CPU consumption is not great, and it's really, really costly. So if you go on the cloud version, it has a cost. If you want to maintain it on your own, on your cloud provider of choice, it also has a cost, of course. So at the end of the day, I find it to be a very good product, has no competition, in my opinion, right now, but has some problems. Let's be honest about that. Before I continue, I want to say that all the problems that I found, maybe it was all my fault. Maybe I was too inexpert and Elasticsearch was a bit too much for me. We all know that making simple software is hard. We can give it a try. But I want this to be clear from the start. I love Elasticsearch. And I started recreating something similar just because I wanted to learn more, not because I wanted to replace, in first place, the whole system. So I set myself a goal. I wanted to give a talk on how full text search engines work. And that's also for another nice reason. If I don't have a goal, I'm not able to understand how stuff works, and basically study. I need a motivation. So that was my motivation, you know? And yeah, I started learning more about full text search algorithms, data structures, whatever. And yeah, I started going down the rabbit hole. So that was me the first few hours reading the theory behind full text search. It's not easy. Let's be honest about that. And the hard truth is that I needed to study a lot of algorithms in data structures. I have no degree, so I didn't have any place in my mind where I could say like, okay, I remember I discussed this during an university lecture. I can reach out to that, professor, for example, for learning something, asking questions. I started literally from scratch, and that can be kind of a problem for us as developers, as I am. But it was very, very interesting anyway. And of course, after you start implementing stuff, after you start at least learning how stuff works, you need to implement it. And of course, when you start implement something, you have to choose a programming language to implement your algorithms and your data structures. And of course, I wanted to be a cool guy. You know, cool guy uses cool programming languages. So of course, no Haskell. No. Of course, I started working with Rust. And I gotta say, I've been working with Haskell for quite a long time, so I thought that Rust could have been a nice option, easiest option possibly. I was terribly wrong. It's not an easy programming language. It's super cool. Of course, cool guys uses Rust all the time. It just wasn't for me. So I decided to re-implement everything from scratch in Golang. And also Golang is not super easy, in my opinion. I mean, when compared to other programming languages such as TypeScript or Ruby, for example, these are another kind of programming language. So I started feeling a bit frustrated about that because, you know, I want to make stuff done, but I didn't have enough knowledge of those programming languages to get stuff done, of course. And then I remembered a quote from Jeff Oatwood, the co-founder of Stack Overflow. As known as the Oatwood Law, that says an application that can be written in JavaScript will eventually be written in JavaScript. And yeah, why not? JavaScript is the king of programming languages, right? So I decided to start implementing stuff with JavaScript. And that was kind of surprising to me. I started implementing stuff with Rust, you know, all the data structures that are required to work on search engines. Started with Rust, re-implemented everything in Golang. Was quite optimized actually because I've spent a lot of time, on Stack Overflow, of course, asking for code reviews to more expert people. So I was pretty confident in the performances. But I gotta say, even though JavaScript couldn't outperform those languages, it was very, very, very close. And we will see how close we are in the next slides. And that brings me to the next question. There is no slow programming language, but just bad algorithms in data structure design, which basically means that maybe my algorithms, of course, I ask for code reviews, I ask for many things and help, but maybe they weren't so well optimized. So Rust cannot make your shitty code be, better. But I have more experience in JavaScript, so my JavaScript code is written better than my Rust code, of course, and performs not better, but we are pretty close, and that's a good point in my opinion to understand. That's a lesson that I had to bring home. So basically, after spending a couple of months working on that search engine, I gave my talk at We Are Developers in Berlin on August, I guess, and yeah, this is how Lyra was born. So Lyra nowadays, it's a open source project that, of course, it's a full text search engine written in TypeScript. And one nice thing about Lyra that I'd like to highlight is that targets every single JavaScript runtime. So it's not a problem if you want to run like JavaScript on, let's say, Node.js, on Dino, on Bun, on Cloudflare workers, on React Native. It's not a problem. We don't have any kind of dependency. We test everything on every single runtime, and we implemented everything from scratch with backward compatibility in every single runtime in mind, as well as performances, of course. So we implemented everything from scratch. We implemented prefix trees, inverted indexes, B-trees, tree maps. We implemented the stamped algorithm, stop words, support for custom stop words. We introduced support for multiple languages, everything from scratch, so that you can use Lyra wherever you want on your favorite runtime. And when I say runtimes, I refer to the fact that you can run, let's say, Lyra on Cloudflare workers or Netlify functions, so you can target edge computing. You can run it on browsers, on BAN, Lambda functions on AWS Lambda Edge, Dino, React Native, Node.js. You can literally run it wherever you want. And talking specifically about edge computing, it wasn't super easy for us to get there. I remember I was in a conference in Berlin a couple of months ago, and I was there with a colleague of mine, and I said, you know what? It would be cool to run Lyra on the edge, right? He told me, okay, yeah, hold my beer. That's all he said, and the day after, we've been able to ship a very basic version of the very first full text search engine capable of running on edge networks. And let me show you how we did it. So, talking about Lyra, how it works, we basically have a collection of functions actually, which are, for example, create, insert, remove, and search. So create creates a new Lyra instance. Insert inserts new data into the existing instance. Remove removes data, and search, of course, performs a search operation. But let's start from the beginning. It's not schemaless, so it's not really like Elasticsearch in that sense, which is totally schemaless, but you have to define the types for the stuff that you're gonna input into the database itself. So in that example, we just create a schema containing author, which is a string, and quote, which is another string. Then we want to insert stuff. So as you can see there, we basically pass the DB, so we mutate the original DB instance by inserting new stuff. This is a synchronous operation, as you can see there. So we also provide an insert batch method, which is asynchronous and doesn't and prevents the event loop from blocking. So that's pretty important, just for you to know. And once we insert stuff, we can eventually start searching for data. So in that example, we pass DB, so inside that database, because we might have multiple databases, why not? Inside that database, search for the term, let's say, if, on all the properties. So search it on quote and author, but you can also choose to search on quote only, on author only. And you will see that elapsed, it's 99, we'll get back later. Count is 2, and 2 results. So these are the results. This is the API for searching data. But now you may be wondering, what is 99? It's seconds, milliseconds? No, it's actually microseconds. And you might be thinking, wow, okay, you only inserted like 4 documents. Of course, it's fast. Yes, this is true, but we also made some benchmarks. So we took 1 million entries, which are actually 1 million movie titles from the International Movie Database. We inserted everything inside Lyra, and we performed different searches. So, for example, we searched for believe inside of all the indexes, and on average, it took 41 microseconds, so millionth of a second, to get all the results. And if you go like in Criminal Minds, for example, it take 187 microseconds. But as you can see, Criminal Minds has 2 different terms, so it performs 2 different searches, then intersects all the documents containing both terms. So there is a lot to do in that case, but it's so damn fast. And again, there's no slow programming language out there. There is just bad algorithm and data structure design. So that's something to keep in mind. After we get there, we also wanted to give support for multiple languages because, of course, English is default, but I'm Italian, so I might want to index Italian data. And when indexing data, we also want to make our search engine smart. So let me give you an example. We perform stemming operations and stop words removals. For example, if we have sentences containing commonly used words such as articles like a, the, etc., and other similar words, we just remove them because they had no sense. And if we have words like lucky, for example, we stem it to luck, so that if you search luck, you will find exactly that word, or luckiest, you will find still all the documents containing luck, lucky. Of course, you can also say, okay, give me the exact result, so luckiest, not luck or lucky. So you can filter out results that you don't want, but we also give you an interface for smart searches. And we do that using a stemming algorithm that right now it's supporting in 23 different languages. So that's an example of how it works. We basically expose a tree-shakeable Italian stemmer. In that example, you can see on the screen. So you choose the language and the tokenizer. So the tokenizer, the stemmer that is part of the tokenizer process right now will be the Italian stemmer. Of course, writing in stemmers is not easy because every single language has different rules. So you can't stem Italian words like English words, for example. We will see more example going on. So lucky gets stamped to luck, but the same rules can't apply for Italian, for example, or Germany, or German, or Russian, or I don't know, Swedish, Turkish, etc. So we relied on Snowball. So Snowball, it's a project created by Martin Porter, which is the author of the Porter stemmer, which is possibly one of the most beautiful stemming algorithms out there, super brilliant, and it's totally open source. So not only the stemming algorithm itself, which is written in C, but can be compiled down to JavaScript or imported into Golang, Rust, wherever. But it also gives you idea on how to create your own stemmer. So in that example, as you can see here, we have like, I don't know, step 0, search for the longest among the suffixes. If we find that suffix, we just remove it. Then next step, search for the longest amongst following suffixes. And whenever we find one of those suffixes, we perform a given operation following the algorithm description. So it's really easy and convenient to follow these instructions to create more and more stemmers that are battle tested, accurate, and also widely used also inside other projects. I'm not sure that Elasticsearch, for example, uses this stemmer algorithm, but I wouldn't be surprised, let's say that. I know that a lot of search engines out there are using the exact same algorithm, so the results are pretty accurate in every other, let's say, competitor we can find for Lyra. So just for giving an example, this is how stemming algorithm works in English. So we have like consign, which gets stemmed to consign. But then we have the past form, so consigned in the past gets stamped to consign again. Consigning gets stamped again to consign. So this is how it works. And of course, I'm Italian. I could write an Italian stemmer, and these are the tests, for example, that I had to perform. I know nothing about German, but I'd love to, but I don't know how to speak it or how to write it. So following the Porter stemmer algorithm description, it was possible to do that. And of course, if you want to have fun, you can create your own stemming algorithm. So in that example, stemming function is nothing more than a function giving you a word and expecting a new word in return. So in that example, we are just appending ish to the word, so that you can, if you really want to have fun or you don't like the stemming algorithm, you can bring your own, which is really, really convenient because there are many out there and you can just import a library and use it as you prefer. So we did also the same for custom stop words. So for example, common stop words are, I don't know, a, the, me, you. These are all stop words that doesn't carry a lot of meaning to the search. If we think of overall meaning for the search query and results. So we basically, given the language that you support, for example, in that case, we don't specify a given language, so it's English by default. We give you the list of English stop words and you can filter them out, you can append new stuff, or you can bring your own stop words. So it's all up to you. So it's highly customizable. Lyra had some project goals, of course. We wanted to run on any JavaScript runtime. We wanted it to be as small as possible, as fast as possible, and easy to maintain and deploy. And I gotta say, we had some great achievement. It works on every single JavaScript runtimes. It has a small modular core. As you can see, you can always interact with the core so that you can You can, I don't know, for example, we have a huge system, so you can interact with all the processes to customize the experience as you wish. It's pretty fast. Can be deployed literally everywhere, serialized data in different formats, so we will see what that means in just a second, and has a powerful plugin system. Speaking of which, at a certain point you have the data, you want to deploy the data, you may want to persist the data somewhere, so you don't have to index everything from scratch every single time, you know? So we created a plugin which is called Plugin Data Persistence. It's an official plugin and basically allows you to export the index from one Lyra instance and re-import it somewhere else. And this is pretty important. Let me show you why. So let's say we have this Lyra instance. We have a schema, we insert data into the original instance, then we import the persist to file function, which is runtime specific. This only works on Bun and Node.js as for now. If there's anyone wanting to implement this on Dino, I'd be super happy to help, of course. And persist to file will return the file path where you persist the data. It's an absolute path. So you pass the original instance that we just created, so this one for reference. We choose the format, binary by default, so message pack, but you can also choose DPAC or JSON serialization, and an output file. So in that case, quotes.msp, which is message pack, of course. So we are basically taking Lyra index, we are serializing it and saving it to disk in a binary format. Then we can use the restore from file from another totally different machine or service, and we read it so in memory. So restored instance constant in that case will be an in-memory index for Lyra. So as you can see, we choose the file quotes.msp, the one we just created, and we can now immediately perform search on restored databases. That brings us to a lot of target architectures. Let me give you a couple of examples. We have the offline search architecture, for example. So let's say we have a mobile app on React Native, which is totally supported from Lyra. So we perform search, and whenever the connection is not established to the server, we can also rely on a local backup for the data. So we can fall back to the local DB that, let's say, every 5 minutes asks the server for new data. So if there's new data, we serialize that new data, we send it to the local database on our applications, and whenever the application, the internet connection fails, we will always be able to fall back to in-memory database, be it, I don't know, SQLite or any database you like to use on your mobile applications. But that's not just it. We may want to have a kind of a CI process for Lyra, so that you build your database every 5 minutes, let's say, or every minute, every 3 minutes, you choose. And you deposit your serialized index on S3, for example. It triggers a simple notification service, SNS, which will deploy some lambdas containing the in-memory index, so that you can query the data directly on AWS Lambda. And every time you put some new index inside S3, you will be able to basically redeploy lambdas and perform search operations on new data. So with that target architecture, for example, you have to forget about cluster management, deployment, data consistency, because it's all managed by AWS in that case. So you only have to take care about performing search operations. Or if you're lazy like me, you can deploy everywhere using Nebula. So I couldn't prepare a real live demo, but let me show you what does that mean. So this is an example. We install Nebula, which is the build system. We install Nebula, which is the build system for Lyra. It's the official one. It's still in beta, but it's working pretty fine. So as you can see, we basically install it from npm. And when we look inside our folder right now in that demo, we have two files, data.json and lyra.yaml. So let's see what's inside those files. If we cat lyra.yaml, we will see that we have a schema, which is a normal schema definition for Lyra. We already saw that. Sharding, automatic, or we don't want sharding. I don't know. That's up to you. an output file, so in that case bundle.js, so it will generate a Lyra application containing the data inside the bundle.js file. The kind of data that we have in that kind is of type JSON, and it comes from the data.json file. You could also use type JavaScript and as a source use, let's say, foo.js, which exports default an asynchronous function so that you can call a database, get the data, and get the data from there, basically, so you can interact with the database. But that's up to you. Let's use JSON, that it's easier. And the target in that case is Cloudflare workers. And we can configure, for example, the Cloudflare worker name, in that case Pokédex, because we are going to deploy a Pokédex. And if we want to run tests, true or false, in that case we want to run tests. If we go see the data that we have inside data.json, as you can see here, it follows the schema definition. So we have a lot of Pokemons, and that's really it. We can now run Nebula bundle, or Nebula D, which stands for deploy. So it will bundle and deploy. And as you can see, in just 5 seconds, we've been able to deploy everything to Cloudflare workers. So if we make a search with this URL for Pika, for example, we will get a response. And we are running on a edge network, in that case, Cloudflare workers. So congratulations. In like 5 seconds, we just deployed the very first full-text search engines capable of running on an edge network. Lyra, it's free and open source. And I will be there if any one of you needs some help setting up it, creating a target architecture. This is a service I can kinda help you with. So if you need something, I'd like to hear from you. I'd like to hear your feedbacks on Lyra. If you have any kind of questions, please feel free to reach out to me directly at Michele Riva Code on Twitter. But we also have a Slack channel where you can find help from a community, from me, from my colleagues working on Lyra. So please join lyrasearch.slack.com. This is where we make Lyra happen. And before I end my speech, I'd like to thank Nearform. We are a professional service company specialized in Node.js, DevOps, React Native. We maintain a lot of open source software. We are responsible for the maintenance of almost 8% of all the NPM modules used globally, which gets downloaded like 1 billion times per month, which is totally crazy. And we are hiring, so worldwide for remote. If you're interested, please feel free to reach out. And I'd like to thank Nearform for letting me work on Lyra and presenting this to you today. So thank you so much. Thank you all for following this talk. And this is where you can find me, mainly on Twitter, because this is where I live most. Thank you again. Has been a pleasure. I hope to see you all very, very soon. Bye.